Bag. Bag.
Can we start, sir?
ಎಲ್ಲರಿಗೂ ನಮಸ್ಕಾರಗಳು. ಕರ್ನಾಟಕ ಸಾಹಿತ್ಯ ವಿಜ್ಞಾನ ಮತ್ತು ತಂತ್ರಜ್ಞಾನ ಅಕಾಡೆಮಿ ಕಡೆಯಿಂದ ನಮ್ಮ ರಾಜ್ಯಾದ್ಯಂತ ನಡೆಯುತ್ತಿರುವ ಪ್ರತಿಭಾಶೋಧ ಕಾರ್ಯಕ್ರಮದಲ್ಲಿ ತಜ್ಞರ ಉಪನ್ಯಾಸ ಮಾಲಿಕೆಗೆ ಎಲ್ಲರಿಗೂ ಸ್ವಾಗತ. ಗುಡ್ ಆಫ್ಟರ್ನೂನ್ ಅಂಡ್ ಗ್ರೀಟಿಂಗ್ಸ್. ವೆಲ್ಕಮ್ ಟು ದಿ ಎಕ್ಸ್ಪರ್ಟ್ ಟಾಕ್ ಸೀರೀಸ್ ಅಂಡರ್ ದಿ ಟ್ಯಾಲೆಂಟ್ ಸರ್ಚ್ ಪ್ರೋಗ್ರಾಮ್, ಎ ಸ್ಟೇಟ್ ವೈಡ್ ಪ್ರೋಗ್ರಾಮ್ of the Karnataka Science and Technology Academy. We have today with us Professor Sarmistha Sahu, a well-known figure in physics communication across the country. And we also have with us esteemed executive committee members of the Karnataka Science and Technology Academy, Professor Basuraj Mulimani and Professor Ambekar Eknath, and my colleagues, Dr. A.M. Ramesh, the CEO of the Academy, and colleagues, Mr. Umesh, and others with us. And a large number of students are joining also online and in the YouTube. Very briefly, Professor Sarmistha Sahu with a master's in physics, and then she's been a professor at the Mani College in Bangalore, and she has been the coordinator of the IAPT, Indian Association of Physics Teachers, across the country, and also specifically for Bangalore. A number of publications to her credit, a number of awards, and also I must mention this national competition of innovative experiments 6 times, and national competition for innovative computational physics 3 times, and then author of several books in physics, Understanding Physics, 8 volumes, and Concise Physics, again 8 volumes. Conducted workshops across the country, hundreds of science demonstrations, interactive lectures, women development centers in physics and in science, and particularly in physics. So it goes on, a lot of voluntary work, and then specifically reaching school students. So it can go on several innovative designs of experiments. And so very happy, madam, to receive you in the academy. And we are aware of your hundreds of, as I said, talks across the country. But today we are grateful that you accepted our request for the student community, researchers, faculty, and seniors in the audience today, online and in YouTube, to have your lecture on magic of pi. And a very interesting title and talk. So with these words, I once again thank madam and request Professor Sarmistha Sahu for your talk on magic of pi. Dr. Sahu.
Thank you. Thank you very, very much, sir. It was really an humbling experience for me to be invited to this wonderful program. And I'm very happy that I will be able to reach out to many more students and teachers across the country, which is my dream. I just enjoy interacting with students. As you've already mentioned, I am running an Anveshika program, which I would like to tell in a few words, because that is the motivator for me to go around talking to students and teachers all around the country. Anveshika is a program which is being spearheaded by Padma Shri H.C. Verma, and we have already 27 such centers all over the country. Ours, Amani IAPT Anveshika, is one at Karnataka, and we try to reach out to students all over Karnataka. That is our dream. Of course, we've never been able to do a good cross-section of the state because of various reasons. And this happens to be a wonderful stage where we can reach out to all the students across the state. And this is a very, very humbling experience for me. Thank you very much to all the team members of Karnataka Science and Technology Academy, and especially to Professor Ayappan for giving me this wonderful opportunity. Thank you very much, sir. I would like to tell you that most of my programs are usually interactive. That is, I do it in the classroom where students are in front of me, or in a teacher training program where teachers are in front of me. And there is a lot of interaction between the audience and myself. Unfortunately, that we cannot do it today. So I'm not sure how it will go, but I always feel that I will try my best and do whatever best I can do on one way. It will become a monologue, so pardon me for that. But I will try to involve students and teachers if they are around. They can send their chat informations, and I will try to satisfy them if I can within this short period. Otherwise, I will leave my email ID at the end of the program. Kindly contact me through email so that I'll be able to answer all your questions regarding this particular topic on pi. I would like to share my PPT first, and then we will talk more about it. So is it okay now?
Yes.
Is the PPT visible?
Yes, ma'am, perfectly.
Okay,
Yes.
so thank you very much. Thank you very much. Okay, now, as sir has already mentioned, the topic for today is magic of pi. What is pi? What it is talking about? How it is prevalent everywhere in the whole globe? I would like to highlight on that and probably tell you a few more activities where the students and the teachers can work on in their classroom. Okay. Now this is a picture where we are seeing the bird flapping its wing. And because of the wind, the flower is also oscillating. The petals of the flower are oscillating. Does it give you an idea that there is pi hidden inside this? I'm sure you can. Please note the flapping of the bird has an angular velocity. The oscillation of the petals has a time period, and all these are having pi involving it. So everything that we look around, we will be seeing traces of pi if we look at it intently, and we will be able to visualize it and make sense out of it very soon. So I go to the next chapter, which is going to talk about pi. Pi, Pi, and not PIE. What do I mean by that? Look at the picture. This is a pi at the left-hand side corner, but I'm not looking at that. I'm not looking at this particular picture. I don't want this. This is the pi that I'm looking at. Okay, so we have now put the pi on the sweet pi, and therefore we will understand how sweet it is all throughout. Pi is a special number. It is a number. We know that there are so many different types of numbers, but this is a special number. Why special? Because it has a symbol associated with it. This Greek letter pi is associated with the number pi, which is 3.14 for short, and therefore it is a special number. It is also written as 22/7. Why it is so, I will have a slide on it. And it is an irrational number. What is an irrational number? If I divide 22/7, then it will be a number which will never stop. It will go on and on and on. The digits will keep on adding. In addition to that, it is also a mathematical constant. That means it does not change in different situations. It remains the same number every time. It is a transcendental number. Very, very funny. It's a transcendental number. That means it cannot be a root of any polynomial if the coefficients are finite. In addition to that, it is intimately connected with circles. And everywhere we look at a circle, we should be able to see that pi is there. It's a very fascinating, never-ending number. Look at the number. It goes on and on. 3.141592 6, 5, 3, 5, 8, 9, 7, 9, 3, 2, 3, 8, and on and on and on and on. I will not be able to stop because it has so many different digits associated with it. It does not stop. We are talking about pi, which children learn in their school itself. And therefore, I'm talking about what children know about it. What is the first circle seen by a baby? All of us know that the child first looks at its mother. And the mother has some circular thing which is fascinating for the child. The child keeps on seeing, keeps on staring at it, getting the pleasure, and I'm sure something in it is giving him the sense of joy and satisfaction. There is a circle in the eye, a wonderful circle, mother's eye. If I'm talking about a circle, this is the circle that I'm showing. We can draw a diameter, and the circle has a circumference. The ratio of this circumference divided by the diameter is equivalent to the pi. Okay. Now suppose I have done one circle. I find out its circumference. I find out the diameter. I calculate it. I call it as pi. Is it true for all circles? Yes. Even if I draw another bigger circle and find out its diameter, the ratio remains the same. Therefore, pi is a constant, no matter what be the shape of the circle or the diameter, because the diameter is fixed for a particular circle, the value of pi remains a constant. If I take a line and divide it, let us say, to 7 parts, I've shown it with small flowers. I've taken a small line and divided it into 7 parts. If this line, I draw a circle so that the line is a diameter, then any one of these flowers, if I take and keep on adding so that all these flowers are covering the circumference of the circle, if you count them, you will be surprised that there are 22 of these when there are 7 of these. And therefore, pi should be equivalent to 22 by 7, which if I divide is equivalent to 3.14. All these figures are not to scale, so please pardon me. With my effort, I tried to do these pictures, but I'm not an expert artist and therefore I've not been able to do it perfectly. So please pardon me for that. So pi is equivalent to 22 by 7, which if I divide it into decimal parts, I will see that it is equivalent to 3.14. Pi, we said, is intimately connected to the circle. But then is it connected to a sphere? Very much true. Because if I take a circle and sweep it around at the diameter, I will get a sphere. Therefore, pi is also related to sphere. Anything that you're looking around, you will find plenty of spherical bodies around. But how do I define, if I'm talking about a sphere, how do I define pi? We know that all spherical bodies have a surface. So if I know the surface area of the sphere, that surface area divided by the square of the disk diameter would also be equivalent to pi. So now we have two different definitions, which leads to the same value pi. If I'm talking in terms of a circle, it is the circumference divided by diameter. If I'm talking about a sphere, then it will become surface area divided by diameter square. If you look around, you will see the sun, moon, earth, planets, all of them are spherical, and therefore they have pi.
Madam, there is a connectivity issue from your side, I think.
Not able to hear me, sir?
No, sir, it's all well going, sir, here.
Can I continue?
Yes, ma'am, please continue.
Yeah, okay. If you look at the around, you will see many circular things. Wheels, which was one of the fantastic inventions of mankind around 3500. That is circular. Coins, which are very, very dear to us. We need it every day in and out. They are also circular. Look at the kitchen. There are plenty of shapes, round and circular. So all these have pi within it. So now I hope you can realize how pi is associated with everything in and around us. So if I'm looking at the moon is spherical and therefore we have pi in it. If you're looking at the earth, both the rotation of the earth as well as the shape of the earth. Both of them are integrated with pi. And there are many more such things. You're looking at the wheel, looking at the coin, looking at all these things. I know that pi is very much involved in these objects. In this picture, we are seeing something going around the globe. What is that? It is a space shuttle. Just imagine the space shuttle is going in a particular orbit and the orbit is visualized over here. What will happen if there is no pi? Without pi, the space shuttle would be an ORI. It just cannot move the way it is showing, or you cannot talk about the orbit without the letter or symbol pi, without the value pi, Y symbol. Okay, if you are looking over the globe, you will find that there are many rivers moving all around the globe. They are starting at some point, going all in curved paths, and finally reaching their destination, which is either the river or the ocean. Look at these. These are not circles. And yet, a very interesting thing was studied by Hans Henrik Coulomb, a mathematician. And he showed you take care of the sinuosity of the river, and you'll be surprised to know that the average sinuosity of a river around the world is equivalent to pi. So you don't have to always have a circle, but there is something circular in it, and that is why it is related to pi. If you look at this river, you can see there is a curve over here, 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 and so on. There is a curve over here, there is a curve over here. So each of these circumferences and the diameter, if you take, and if you average it out, you will find that it is equivalent to pi. So pi shows up even at strange places in meandering paths of rivers. So it's very surprising that I was talking about only circular and spherical things. Now you can see that happening also in rivers. So the history of pi, if you look at it, you'll be surprised to know that 4,000 years back, people were aware of pi. And we will see certain eras where the different values of pi that they were taking. In these 4,000 years, how many seconds are there? Calculate. It is a huge number. Even all the numbers in the second of 4,000 year is not sufficient to give the value of pi accurately. At present, we are aware of 31 trillion digits by which pi can be expressed. But there are many more. I don't know when or how, when the people will be able to give us even better and better digits after 31 trillion. So we will look out for it, and it is fun to find out all the different ways people work on it to find out more and more digits. Some of them I'm just going to mention right now. And pi was named, like how a child when he is born there is a naming ceremony. Pi was also named in 1706. A British mathematician, William Jones, this is the picture of William Jones, gave a symbol to pi, and this Greek letter represents pi. So that was a naming ceremony. And after a few years, in 1737, pi was popularized by the Swiss mathematician Leonhard Euler. I'm sorry, there is some overlap, so I'm telling you the names. Leonhard Euler. And Leonhard Euler is not only a mathematician, he is also a physicist, astronomer, geographer, logician, and studies of graph theory, topology. A fantastic work he has done. So he popularized this symbol so that now we use pi as the Greek letter. There is a pi day. All of us know that we have a birthday, we have an anniversary, some special days. Pi also has a special day for it, and it is known as the pi day. Why do you think it is there? None of the other numbers have any day associated with it, but pi has. The Americans call March 14 as 3.14. And the value of pi is equivalent to 3.141592, etc. on an average, we use these 3 digits only, significant figures, 3.14, and therefore March 14th is known as the Pi Day. And there are many admirers and enthusiasts who celebrate pi in a fantastic way. The whole world is full of fields and forces, and I'm aware of it, that all the children are knowing that there are many forces which are acting on the in nature, which is giving rise to the physical status of the existence of the universe. So what are these fields and forces? Why are we associating with these fields and forces? Very nicely it will be observed that when I'm looking at the electrical world, the electrical world is made up of charges, positive and negative charges. If you look at a positive charge alone, you will find that it is having a circular field around it, which is going outwards. If you look at the negative charge, you will find there is a circular field again, but it is pointing inwards. No matter what, since they are circular, positive and negative charges will attract each other. Positive and positive charges will repel each other. Negative and negative charges will repel each other. So these forces of repulsion and attraction are given by Coulomb's law, which states that the force is equivalent to the product of the two charges divided by 4 pi epsilon naught r squared, where epsilon naught is the constant of the medium, r is the distance between these two charges, q1 and q2 are the two charges. Okay, so again there is pi over here. So if you are talking about electrostatic forces, there is pi involved in it. If you look at the gravitational world, the gravitational world is also associated very intimately with pi. We know that according to Einstein's relativity, general relativity, he has mentioned very clearly that the space-time of the gravitational field is having curvature. What sort of curvature? The curvature depends upon the mass and the energy which is filled in the space. And how does the mass and the energy move, or at least mass move? The movement of the mass depends upon the curvature of that point or that area drives the mass, and they are intimately related to each other. So if I just want to have a show of what it exactly it means, suppose I'm looking at a mass over here, and this is your space-time around it, then I want to show you how it is. I'm not able to do it. I'm sorry. It's not moving. When this moves, the entire structure moves over here. And therefore, it shows that the space-time around it is affected by the movement of the matter. Unfortunately, I'm not able to show it over here. I'm sorry for that. Okay. Now, what are the values of pi? I said that pi is equivalent to 3.14 is the value that we usually use. But is that the value that was being used all 4,000 years? We'll just have a look into it. What are the different values that were being used at different times in the history of pi? Babylonians around 2000 BCE used the value of pi as 3.125. How did they derive it? They took a hexagon which was inscribed inside a circle. Hexagon is having straight lines, and therefore it is easy to find out the perimeter of this hexagon. They assumed that the perimeter of the hexagon is 24 by 25 times that of the perimeter of the circle. And from that, since this perimeter can be determined, they found out what should be the approximate value of pi, which turns out to be 3.125. So therefore, in this period, the value of pi was used as 3.125. On the other hand, in Rhine Papyrus, in the year 1650 BCE, not year, approximately 1650 BCE, the Egyptians were aware of pi, and they found out the value of pi from this ratio, 256 by 81, which is equivalent to 3.16045. I just want to show you that yes, they were aware of this. Why did they take this value? where did they get this value from is very clear from the wonders of the ancient world, the pyramid. This is the pyramid which Egyptians are fond of building. And if you look at any one of the pyramid, I'll talk in terms of the Giza Pyramid, which is one of the wonders of the world. In the Giza Pyramid, if you have to look at it carefully, you will find that this base area is equivalent to 1760 cubits. So I'm talking about the base of the pyramid, which is square. It is equivalent to 1760 cubits. On the other hand, if you look at the height of the pyramid, that from this tip to the bottom, height of the pyramid, it is equivalent to 280 cubits. And therefore, if you find out the ratio of this area divided by this height, it turns out to be equivalent to 6.28. So what? We never saw this number before, but luckily 6.28 is equivalent to 2 pi. Therefore, you will look at the pyramid and you will know that they were aware of this pi. Their entire construction of the pyramid was based on this, and their calculation was done in a fantastic way. We even see the pyramids existing till today in a wonderful way. In fact, the Giza pyramid itself is intact till today. On the other hand, what are the other values people were using? I'm showing you. Archimedes of Syracuse found out very patiently the value of pi, not exactly the value of pi, but the upper and the lower limits of pi. And from that, he told that the value of pi is equivalent to 3.1418. Look at the number, 3.14. That means he has done a very good calculation to find out the value which today we claim is the value of pi approximately. Okay, how did he do it? He inscribed a polygon and he circumscribed a polygon about a circle. So he took a circle and he inscribed, let us say, a square over here and circumscribed another square over here. Once you have done a polygon, regular polygon, it is very easy to find out the perimeter. So you know this perimeter, you also know this perimeter because you know the dimensions of this and this. Once you know the perimeter, this perimeter or the circumference can be calculated or said to be in between this perimeter and this perimeter. Therefore, the circumference limits, upper limit and lower limit can be found out. From that, you can say since the circumference is within this and this, the pi value should be within this and this. Now, if you draw a polygon of this type, let us say with 4 sides, then you realize that this length is very much different from this. Similarly, this length is very much different from this. Therefore, the range will become very, very large and the value will be very inaccurate. So he did it patiently for 6-sided figures, for 8-sided figures, 12-sided figures, and many more till he came to 96 sides. Just imagine 96 sides of the polygon. It is increasingly difficult to find out the perimeter as the number of sides increased. But he did a calculation and found out the perimeter of the circumscribed as well as the inscribed 96-sided Anakota Kai hexagon. That is what it is called. And from that he mentioned that pi should lie between 223 by 71 and 22 by 71. And the average value of that he mentioned was equivalent to 3.14. We acknowledge it and we have also used different methods. In fact, many different mathematicians have been finding out different methods of calculating pi, which is very close to 3.1418. He, in addition to the value of pi, also mentioned that the ratio of the area of a circle to the square of the radius is a constant. Please note this. It is ratio of the area of the circle, this whole area, not the circumference, divided by the square of this radius must be equivalent to a constant. And from that, the area of the circle is told to be equivalent to pi r squared. There are many different values of pi calculated by very many people. There were Chinese, Indian, Arab mathematicians who found out the digits more and more by tedious calculation. One of them, the Chinese mathematician by the name of Liu Hui, found out the value of 3.1416, again very close to what Archimedes had mentioned. In the end of 17th century, there were new methods found by European mathematicians, and they used the infinite series. I will talk about at least one of them, if not everything. And in the 18th century, there was a gentleman known as Georges Buffon, a French mathematician, who devised a totally different method of calculating pi using probability. So there are so many different ways of calculating pi. I would like our children to also make sense of this and try to calculate pi themselves by at least some method. I will try to show at least one or two methods by which you can calculate, and it is fun activity. It is a lovely game. You will enjoy doing it and feel very satisfied that yes, you can also calculate pi by different methods, like all the great mathematicians who have suggested different methods, calculations, mathematical analysis to give the value of pi. There are many other novel methods. I just want to make a mention of it. Sir Isaac Newton used the binomial theorem. Okay, a great mathematician, Indian mathematician Srinivasa Ramanujan used exceptionally efficient ways to find out the pi. I will talk about it in a few minutes. And luckily, since his method was very efficient, it has been incorporated in computer algorithms. So right now, a computer is working on this method by which Srinivas Ramanujan has suggested, and it is known as a pi calculator. Of course, there are even other better methods because of which we are able to find out 31 trillion thing. But this is one very good method which can give you not so many digits, but very nicely it can be a thing. Finding out the value of pi if you gradually increase the number of digits. I'll just show it to you in a few minutes. In 1949, John Newman actually used a computer called the ENIAC computer and found out the value of pi to 2037 digits, which is a huge number of digits at that time in 1949. It was the first time computer was used to find out the value of pi to so many accurate digits. In the early 21st century, computers calculated pi up to, God bless you, 31 trillion, 415 billion, 926 million, 535,897 decimal places. Just imagine the number, how big it is. It's almost approximately 31 trillion digits. And if you write the same value of pi in a different form, not in decimals, but in binary, zeros and ones, you will have even larger number of digits. 2 quadrillion, I don't know how big it is, but it is that many digits which you will be using to write the value of pi. Buffon's needle, how it can be determined, how it was determined in those days, I just want to highlight on that. This is a wonderful way which can be done by the students, and therefore I would like to spend a few minutes in this also. Buffon's needle is started as a game. All of us stay in houses which are tiled, and all these tiles have lines, parallel lines on it. So suppose we take a number of coins and then put it on the floor, we will find that some of these coins will touch the line while the others will not touch the line. Okay, we can make an estimate of how many coins were put, of which how many of them are touching the line. And from that, you will be able to find out the value of pi. Wonderful game, very easy. Instead of using coins, actually in Buffon's era, mathematicians Mario Lazzarani used needles, and therefore it is known as the Buffon's needles activity. Okay, it was using the probability the probability was determined using Monte Carlo simulation, and therefore we call it as the Buffon's needle by Monte Carlo simulation. A French philosopher by origin, his name was a huge big name. He had got a particular what do you call it? Comte de Buffon was given his, I'm not able to get the thing, and he generalized this game. So if whatever game I was telling, he generalized the game and explained how exactly the probability will give us the value of pi. So if you consider the needle length is equivalent to the two lines, suppose I take a needle this big and the line separation between them is equivalent to this big, then it can be shown that the probability is directly related to the value of pi, which is equivalent to 2 times capital N by small n, where capital N is the number of needles and small n is the number of needles which are cutting the line. That means if you throw these needles, some of them will cut this line, some of them will fall like this and not cut the line. The number which is cutting the line, if it is equivalent to small n, and the total number if it is equivalent to capital N, just the ratio of that multiplied by 2 will give you the value of pi. Very easy, and therefore we can try it out. This experiment was done by Mario Lazzarini. He threw 4,000 times that needles, and from that he calculated the value of pi. It's not just one time, because if you do it one time, you will not be able to give the value of pi accurately. There will be error. So he must have done thousands of times. 4,000 times he has taken the needle and he has found out. So from that he calculated the pi to 6 decimal places of 120 years before. Now, to just talk in short about how to calculate the probability, I'm just showing you over here. Suppose I say that there are two lines and this is a needle of length equivalent to L. If I randomly throw the needle might be anywhere. It may be like this, it may be like this, it may be like this, it may be like this. I'm considering one particular needle, let us say of length L, which is cutting this line at an angle equivalent to theta. If the length is equivalent to L, then the vertical component of this length will be equivalent to L sine theta. If it is cutting a line, then from one of the tips of this needle up to the line, if I call it as D, we can see that only when D is smaller than L sine theta will it cut this line. If D becomes greater than L sine theta, that suppose this was D and this was equivalent to L sine theta, then there is no way that the needle can cut the line. Therefore, the condition is for the line to be cut by the needle, the distance, the vertical distance from the tip of the needle to this line D should be lesser than L sine theta. If that is so, then the largest length can be equivalent to L because sine theta maximum value is equivalent to 1. Therefore, D should lie between 0 and L. And what is the value of theta? If this angle is equivalent to the inclination theta, then the needle can fall like this, the needle can fall like this, the needle can fall like this, the needle can fall like this. Therefore, the range of theta will be between 0 and pi. So under these conditions, if you plot a graph of D versus L sine theta, then the area which will cut the line will be given by the picture which is pink in color, while D will have maximum value equivalent to L, and for all angles from 0 to pi it will be equivalent to L, and therefore the corresponding area will be a rectangle shown by the blue picture. So how do I find out the probability? Probability should be equivalent to this area divided by this whole area. If we can find out this area, then it is very easy for us to tell what is the probability and from that to calculate the value of pi. Now, any area can be determined by integrating it. That is the meaning of integration. Therefore, if I take L sine theta and integrate it between the limits 0 to pi, I should be able to find out this pink area, which I've done it over here. So integration from these two limits, L sine theta d theta. It's a simple integration. You can simplify it and calculate. It will turn out to be equivalent to 2L. Therefore, probability is equivalent to the pink area divided by the blue area. Area under the curve divided by area of the rectangle. If the rectangle has this length equivalent to L and this length is equivalent to pi, the area should be equivalent to pi times L, and therefore 2L divided by pi times L should be equivalent to the probability. L is common and therefore the probability is equivalent to 2 by pi. How do we define probability for any event? The number of events that has happened by the total number of events is equivalent to probability. So general definition says if small n is the number of needles which are cutting the line and capital N is the total number of needles which were thrown on the area or domain, then n by capital N should be equivalent to probability. And just now we showed that probability is equivalent to 2 by pi. Therefore, n by capital N should be equivalent to 2 by pi. And from this, we can calculate pi is equivalent to 2 times n by small n. But please note, this is only true when the length of the needle equals the distance between the two lines. That means there is a constraint. I'm saying that if the two lines are equivalent to L, then the length of the needle should also be equivalent to L. Then only this condition holds good. So we have to take care of that when we are using this formula to make sure that the needle length is equivalent to the separation between the two lines and then use this formula. But it is not correct because when we were using the coin, I'm sure you can't have a coin which is that big, which is going to be equivalent to the separation between the two lines of your tile. And still you can find it out. And therefore, there should be a way out to find out. Suppose I say that the length of the needle is not equivalent to the separation, but it is smaller than the width of the line. I'm calling the width of the line as capital K and the length of the needle as capital L. Then it is very clear that if I have two lines like this, if the length of needle becomes longer and longer, then the chances of it cutting the line will become greater. And therefore, probability should be directly proportional to the length of the needle. On the other hand, if I have a fixed needle, but I have this separation once like this, next time I have a separation over here, next I have a separation over here, then the chances of cutting this needle will become lesser and lesser as K increases. And therefore, the probability must be inversely proportional to K. So from this consideration, we can say that the probability is equivalent to 2 times pi multiplied by L divided by K. That is how I've written probability over here if L and K are not equal. And under this condition, we can also find out the value of pi very easily, which will be equivalent to 2 times capital N and capital L n divided by K times small n. And here you can find out that the value of pi can be simply calculated if you know the length of the needle, you know the separation between the two lines, and throw these needles at random. So it is a random phenomena, and count the total number of needles and the number of needles which are cutting. But look at this. When we started, I mentioned that pi is related to a circle or a sphere. But where is the circle or a sphere over here? So we can calculate pi even when there is no pi, circle and sphere. But you should be able to tell me by now that where did I get this pi? Please look at this. Where did I get this pi? Okay, L sine theta. So trigonometric functions are also associated with pi, which are of course offshoots of circles, and therefore you can calculate pi even if the circle or the sphere is not visible. It is inherently included in the system. Okay, now this is a simulation which I have taken from the internet and I'm just showing it to you. Here the Buffin's needle experiment is being simulated, and from that you can actually count the value of pi as the number of needles are gradually increasing. I'm just telling you how it has been shown. This purple color needles are the lines, needles which are not cutting this line. This is a line, this is a line, this is a line, this is a line, and so on. When you put it at random, the purple color needles are not touching the line. But on the other hand, the blue color needles are blue or green, whatever you call it, are touching the line. Therefore, since it is automated, you can calculate the number of needles which are cutting the line and the total number. That is mentioned over here. The throw number means how many needles were thrown at a time, and gradually it increases from 0 to 999. That means at 4, 5, 6, 10, 20, 30, 40, 100, 200, up to 999 needles, what is happening, we can find out. And here the length of the needle is given to us. The length between the two boards are given to us. The number of lines, needles which are crossing the line is mentioned over here. And the number of throws, that means the total number of needles, is also given over here. Gradually it is changing because the number of needles that are being thrown is gradually increasing from 0 to 9. Each time the value of pi is being estimated, and if you look at this number, it is always a number very close to 3.14, but definitely not equivalent to 3.14 every time, which means obviously for random phenomena, you cannot find out the value of pi accurately. It will fluctuate, but it is fluctuating within some limits, which is a fairly good uncertainty that is mentioned in the experiment. To see what is happening, there is a line over here which tells us that the value of pi is equivalent to 3.14. And what happens when the number gradually increases from 0 to 999? And the pi value is being plotted over here. Sometimes the pi value is above 3.14, sometimes it is below 1 per 3.14. And gradually the number of needles are increasing. You will see that when the number of needles were small, the error was very, very large. But as the number gradually increases, the error has become smaller and smaller. And as it becomes more and more and more, the uncertainty becomes even lesser and lesser. So this very clearly tells us that obviously when you are taking just 10 or 20 needles and trying to doing the experiment, you may get the value of pi somewhere close to 3.14, but definitely the uncertainty will be very, very large. Instead of taking 10, 20 needles, suppose you take 10 million needles, 20 million needles, then the value of pi will become even better, and therefore the uncertainty is shown lesser over here. So if you are going to do the experiment, what would you choose? Obviously, you would need to take large number of needles so that you are able to get the value of pi very close to the estimated value. Okay, and therefore many a times it may not be very easy for us to take needles in our hand and then do it the thing activity, though Lazier has already done it for 4,000 needles, which must be a cumbersome thing. It is very difficult. And therefore, it is always better if you want to increase the population, have the number of needles large. It is better to do it with the help of computer and some sort of simulation so that you will be able to get the calculations immediately without much effort. But at the same time, get the pleasure of calculating what is the value of pi, what is the uncertainty, how can you increase or decrease the uncertainty, how can you make the values as close as you wish, etc., can be learned from these simulations if you do it yourself. And I would suggest that you do it yourself. Okay, I want to show you one of these videos, how it can be done, or I will not show it to you, I think. I'm just telling you, just take a graph sheet, make some parallel lines, take some matchsticks which can be cut so that the length of the matchstick is exactly equivalent to the parallel lines. I'm not showing you the video, but I'm telling you. Then you keep throwing 10, 10, 20, 20 matchsticks, count the number of matchsticks which are touching the line. From that, since the length of the matchstick and the separation between the two lines you have done are equal, you can simply count the number of lines which are needles or matchsticks which are touching the line and the total number of matchstick, and from that you can find out the value of pi. I've shown it in the video, but I thought I will not show it to you right now. But I would like to show you the spreadsheet which can be shown over here, how it can be done. Okay, so just a few more minutes I will spend in doing this and then I will go ahead. Okay, now if you see this carefully, this is called a spreadsheet. All of you, those who are using computer Windows, have this in your laptop and you can use it. It is an Excel sheet, and using Excel sheet, you can very easily do these calculations. All these calculations, functions, etc. are there very neatly in the spreadsheet itself. You can calculate. I'm not showing you how the calculation is done, but I'm just showing you, this is my graph. These are my needles and these are the lines. I have calculated it for a huge number of needles. I can tell you exactly how many needles I've taken. It's 300 needles over here. Okay, not really huge, but then 300 needles. And I will just show you what happens. From that 300 needles, you can calculate the value of pi. I'm showing you the values over here. But before I show you the values, I will show you. This is one value of pi. Okay, How many needles are cutting this line? I can calculate. I don't have to calculate. The computer will do it. I have to simply give the commands and it will do it. And it will tell me how many needles have been cutting this of the 300 that are there. And from that, I'm calculating the value of pi. But that is not enough. I need to do it repeatedly. If I do it in hand with matchsticks, it is going to take me ages. I will gradually become very tired and then I will lose interest. But here, if you do it once, the value of pi is determined. I can do this in n number of times. Each time I make a click, I'm getting another setup. Again, it is randomly thrown on this platform or the domain, and how many are cut, it is going to tell me. Again, I have found out the value of pi. So simply by clicking just one click and I know the value of pi. One click and I know the value of pi. So that is so simple if you use a spreadsheet and do the simulation. Okay, I wish all of you take pains and find out how to use a spreadsheet, especially Excel, because it is free and it is there with you, and find out the value of pi. So here I have just tabulated for the sake of simplicity. When I take 3000 needles, the length of my needle is equal to 0.8. 147 of them cut, and the distance between the two lines was equivalent to this. I got 327. The uncertainty over here I have also calculated. I've given the formulas over here. It is equivalent to 0.2. But if I calculate for 200, then pi value is equivalent to this much, but uncertainty is this much. If I use 100, then the pi value is equivalent to this much and the uncertainty is this much. Pi value is going to be random every time. I'm just showing it to you. With the click of a button, the values have changed. Click of a button, the values have changed. Click of a button, the values have changed. That means that many times I can find out. But look at the uncertainty. Every time I'm getting the value of pi close to 3. Okay, not very far. It is, of course, plus or minus, but the uncertainty is 0.2, 0.3, 0.4. Please note that there is a gradual increase in the uncertainty when the number of needles is gradually decreasing, which clearly shows that if I keep on increasing the number of needles from 300 to 3 million, the uncertainty will become very, very small. And that should be our attitude whenever we are doing an experiment, to find out the value as close to the expected value as possible. So we have to find out the methods by which it can be done. Just now I was mentioning that by a click of a button, I can find out the value of pi. This is for 300, one value, one uncertainty. One value, one uncertainty. But if I want to find out for 300 many number of times, I've written the values over here. I have, each time I click, I find out the value of pi and have written all the values of pi, or 10 of them. It shows very clearly that the value is going to be lesser, sometimes more, sometimes less, sometimes more, and so on. But the average value, when you look at it, you need to do the experiment many more times, because your average value will be very close to the expected value. Look at my average value, they are close to 3, even though my some individual values were 2.8, somewhere it was 2.7, somewhere it was 2.9, somewhere it was 3.56, and so on. You need to repeat the experiment many times if you want a good average value. All the average values are close to my expected pi value. And if you look at the value of the standard deviation, I'm not able to show you. The standard deviation over here, I'm sorry, I'm not able to move it, is again gradually decreasing when the number is increasing. For 300, it will be less. For 100, it will be more. So the standard deviation also shows that it is always advisable to use large number of needles. And since we need to use large number of needles for all random phenomena, it is better we do it with some sort of automation, though it can be done in the classroom by students using only 100 matchsticks. It would be a pleasure if the children do the experiment with the matchstick, with 100 matchsticks, let us say, and then go to higher mechanisms where they can use simulations and find out the value of pi. Then they will be able to acknowledge that these are good ways, these are not so very good ways, and therefore we should adopt one of these methods for calculating any value in an experiment. Okay, So next, I would like to tell you a few things about Indian values of pi before I close. I've taken 3 old Indian values of pi from these 2 Vedic literature, Satapatha Brahmana and Bodhayana Sulba Sutra, which I have written it as SB and BSS because I am not very clear or not really pronouncing it properly. Therefore, I don't want to continue making end. Okay. Now, these Vedic literature shows that the squares were transformed into circles of equal areas, and from this, the Vedic altar construction was made. That means we have all these fire pujas. All those altars were made using this scheme in practice, where the squares and the squares were converted into circles, and they were almost having equal areas. And from that, we will see how they were aware of the value of pi and used that knowledge to construct all these altars. So this is one of them I've taken from the internet, which is about 4,000 years old from the Wikipedia. These I have taken from Subhash C. Kak's journal literature, where he has published this 3 old Indian values of pi in Indian Journal of History of Science. One of them is like this. It's called the Garhapatya altar. They were taking 4 bricks, keeping them one after another in a particular direction, and then taking smaller bricks, 4 of them, keeping it on either side. This was enclosed inside a square. Since there were 4 bricks over here, one such calculation shows that each of these bricks were of dimension 48 by 24 angulas, while these small ones were 24 by 24 angulas. And they called this as the body of that human being. And these are the arms, and these are the thighs of the human being. So they were considering Devata's picture over here while making the altar. And this area was defined because this length was also known, and this length was also known by the dimensions of the bricks. If you consider the area of the circle is equivalent to 1 Purusha, which is a unit of the Vedic times, which I will tell you now. If you consider this circle to be equivalent to 1 Purusha, then the length of this square was equivalent to 4/5 of a Purusha, and therefore the area of this would be equivalent to 4/5 into 4/5 Purusha square. If we look at the square, you will realize that the diagonal opposite corners are touching the circle. Since this length is known, you can always find out the diagonal, which is equivalent to √2 times A. Since A is known, √2 times A is equivalent to root of 32 by pi. And luckily, that diagonal is also the diameter of the circle. And therefore, you know the diameter of the circle. Once you know the diameter of the circle, today's calculation we can use and find out the area of a circle is equivalent to 1 Purusha, we said. So 32 by 5 squared is pi by 4 should be equivalent to 1. Taking this into consideration, it can be calculated that the pi was equivalent to 3.125. And therefore, they were aware of the value of pi, and they were constructing these altars which was satisfying the value of pi. In this case, 1 Purusha is equivalent to 120 angulas, and the bricks were each 48 by 24 square angulas and 24 by 24 square angulas. So all these units, I've just lifted it up. I'm really not aware exactly how to convert it into inches or centimeters, so I will not mention that. This was an excerpt from the Satapatha Brahmana, where it is written in Sanskrit, which I will not try to read, but it says over here whatever I was telling. He puts on 4 bricks running eastward, 2 behind running crosswise from south to north, 2 in front. Now the 4 which we puts on running eastward are the body, and as there being 4 of these, it is because the body of ours consists of 4 parts. The 2 of the back then are the thighs, and the 2 in front are the arms, and where the body is, that includes the head. This is a translation by Egglings, which I have just lifted from there. So this is another way of doing calculating a circle from a square, and hence find out the pi. I'll just tell you in short. A square over here was such that the area of the circle was equivalent to the square. This square was having a dimension of 15 by 15 units, and this diameter was 2 units more. That means it was equivalent to 17 units. Since you know the diameter and you know the area of this is equivalent to this area, you will find out the diameter square pi by 4 is equivalent to the area of the square, which is 15 squared. And from this, you can calculate the value of pi. Therefore, pi also shows over here that it is equivalent to 3.1 volt. And therefore, this construction also was done keeping in mind the value of pi. This is again a translation. I'm not going to read it. And there were also other things which were being done those days, which satisfies the value of pi. One of them is a wheel Ratha Chakra. Here again, the same square and the area of the circle are taken. And from this, they have calculated. In this case, the square was having a dimension of 17 by 17. And the diameter was 2 units more. Again, 19. And using that value, the value of pi is determined as 3.20. Okay. And other things which are very, very interesting is Madhava's series. Madhava was an Indian mathematician. I just want to, oh, God. I'm sorry. I thought I will make it bigger so that you can see it without realizing that it has gone off to the first page. Okay, Madhava series. Madhava was a Sangamagrama of 14th century. Okay, Kerala thing. Origin was Kerala. And he had done wonderful mathematics. He had also mentioned infinite series. We were talking about infinite series. The value of tan x, tan inverse x can be given in terms of the series, which is an infinite series. This was written by him in the 14th century. But later on, Leibniz gave another thing, infinite series, where he said that pi by 4 is equivalent to this much. But if you look at it intently, you will realize that this is a special case of a general formula. Madhava's formula was a general formula. Leibniz formula was when x is equivalent to 1. So when x is equivalent to 1, this series is in this form. And if I put x is equivalent to 1, tan inverse of 1 is equivalent to pi by 4. Therefore, pi by 4 is equivalent to this much. Hence, it is now known as the Madhava-Leibniz series. From this, you can calculate the value of pi very easily when you substitute. The value of pi will become better and better as the number of series becomes more and more. So this, because of its multiple authors, you will find that this particular series is known as the Madhava-Newton series. It is also known as Madhava-Leibniz series. It is also known as the Leibniz formula for pi or Leibniz-Grigori-Madhava series, etc., etc. This is because the Western discoverers were trying to either discover different ways, which were, of course, similar to whatever was done, or they were trying to popularize these series, and therefore it is named differently in different periods. Another great mathematician of Indian origin is Ramanujan. He had given again infinite series in 1914, 20th century, beginning of 20th century. Luckily, he had given two such series very similar to each other at the same time, and therefore it is known as Ramanujan 1 and Ramanujan 2. In this series, if you see carefully, you will see that 1 by pi is equivalent to this series. Again, it is an infinite series. N is equivalent to 0 to infinity, etc., etc. So these series are being used for finding out the value of pi in use calculators. And these two series show you that this series becomes closer to or converge very fast as compared to this series. Later on, of course, in 1987, Chudnovsky gave another series similar to him, but it was converging even rapidly. Okay, I think I will stop now because it's not correct for me to go on. It's 5:03 and therefore I thought I will stop. But this is just a simple experiment. Students can do it in the classroom. Just make a circle inscribed inside a square. Take similar side grains and spill it over it. count the number of grains present inside the circle, count the number of grains totally. And if you see it carefully, you will realize that the number of grains falling over here would be proportional to this area, while the number of grains falling in this square would be proportional to that area. Therefore, the number of grains inside the circle by the square would be equivalent to area of the circle by area of the square. With your simple calculation, you can show it is equivalent to pi by 4. And therefore, pi can be calculated simply by knowing the total numbers. I will not like to tell any more anything else. So thank you very much. Okay. Thanks a lot for your kind and attention. I think we'll stop and then you can ask me questions if you like.
Madam, thank you very much for a very insightful and scholarly talk on pi. We did not know that there is a lot of history behind pi. We were not in fact, we were not told in the classroom also, and we did not venture also to look into the history. Very great talk, madam. We are very thankful to you for your wonderful talk. We have with us former Vice Chancellor of Gulbarga University, Professor Mulimani sir. Over to you, sir, for your words.
Professor, thank you very much for the very interesting talk. You have made it very interesting to students. Usually students think mathematics is something not so interesting. And you have shown it, how a simple thing like pi, circumference of the circle and diameter, pi can be calculated in so many ways which students can do themselves, which great people have done through various things like Ramanujan. You have shown it, it's a wonderful thing. By doing, they develop a love for mathematics, and students have also come to know how an entity like pi enters in many places. For example, sometimes somebody said this pi enters in this population distribution functions. Population distribution. Somebody asked, how come, population has to do circumference of the circle divided by the diameter? It's a fantastic thing. You have made it very interesting. And students come to know that if anything is pursued wrong, starting from the simplest way to the things, it leads to many wonderful things, and they develop interest. Depth leads to many. For example, if the pi enters in chaos theory, at what decimal places if you take pi, whole thing changes. Thank you very much, Professor.
Thank you very much, sir, for your kind words.
Thank you.
It was real fun.
You made it very interesting to students. I'm very happy. Thank you.
Thank you, sir.
Thank you, sir. Now we have with us Dr. Ambekar Eknath, sir, former Director General of NACA and esteemed member of KCA. Sir, for your words.
Yeah.
Eknath, sir.
Madam, I wish to echo what Dr. Molamani, Professor Molamani said. But thanks to you, I learned what is pi at the age of 65.
Oh, God. So also me. So it's
Thank
not
you very much, madam.
something that I had
Thank you.
spent so much of time, because I plan to do some workshops with the children and to see them excited about certain things. I delved into this and I've learned much more than what I had learned when I was actually teaching. It's very
Anyways,
true.
Since I have retired, then I will try to do the spins and needles experiments. I have a lot of time on my at my disposal now. Thank you
Yes,
very much, madam.
yes.
You have put some
Thank you
nice.
so much.
Yeah, it was very interesting. Thank you.
Thank
Thank you
you
very
so
much.
Thank you very much, sir. We have with us Srimati Uma madam. MK Uma madam is with us. In fact, madam is instrumental in introducing Sarmistha madam to us. She has joined this talk. Madam, would you like to say something about the talk?
Namaste. Thank you. Good evening, everyone. Bhala interesting agittu. It was a very interesting topic, and every time I have been with her when she was doing this experiment with the students. Every time I attend that, it was so exciting. I had gone back to my younger years, as exciting as it is today. Thank you.
Thank you very much. Uma has been a part and parcel of Amani Anveshika, and we work together. It is a pleasure working with Uma ma'am. She is very dynamic, reaches out to the children, talks to them in their language, and makes me comfortable in the classroom. Thank you very much, Uma, for introducing me to KSTA. Thank you for this opportunity.
Thank you.
Mr. Umesh, any questions from audience?
No, sir, there are no questions from the audience. We have requested them to send if any questions in future. They can mail us or they can contact us. Then we'll get back to madam and revert to them.
Madam, I think this Aryabhata also calculated, I think,
Sir?
Yes.
in 499 or something AD, Aryabhata.
Yes.
So the Indian contributions way back.
There are very many contributions from different corners of the universe. Universe, right? World.
Thank you.
So once again, thank you very much, madam. It would be very nice if we can organize an offline workshop with madam. I'm sure in the coming days we'll have offline workshops for school children as well as for undergraduate and PG students. We'll have both you and Uma madam for workshop. We'll have our students. I'm sure will get a better understanding of how to calculate pi in the coming days. Once again,
Thank you very much, sir. We'll
Professor
be looking
Ramesh, it
forward
was so
to this.
nice.
Yeah.
Yes, sir.
Professor, both of you, Uma Madam and you, Professor Uma Madam gave a wonderful talk on pendulum. And you gave a wonderful talk on pi. You form a mathematics physics combination extremely well. Thank you too.
Thank you, sir. Thank you very much. Thank you
Uh,
very much for giving us this wonderful opportunity. To
Sarmistha
the entire team of KSTA.
for being with us in this wonderful workshop. Thanks, madam. We'll be inviting you again for offline workshop. You should grace the workshop in future as well. I'm thankful to Professor Mulimani sir, who has been with us since afternoon, and he has been a source of inspiration. He always been in every lecture and inspires us. Thank you very much, sir. So also our Dr. Eknath sir, he also will be with us in all the workshops and encourages us. Thank you very much, sir, Eknath sir, for being with us. Our source of inspiration again, Professor S. Ayappan sir, chairman of KSTA. He picks up good speakers from here and there and introduces us. We are grateful to you, sir. Thank you very much. We are grateful to Uma madam for introducing Sarmistha madam. And also on the other day, she delivered a wonderful lecture on pendulum. Thank you very much, madam. We are thankful to all the senior faculty and students who have joined on Cisco WebEx and YouTube platform. Thank you very much. We'll be intimating you about the future talks in a few days. Until then, goodbye. Take care. Take care. Thank you.